Welcome everyone to this first in a series of videos on Archimedes on the sphere and cylinder. This work not only contains his discovery of the formulas of the surface area and volume of a sphere in terms of its radius, but it also explores cones, segments of spheres, and also how a sphere compares to a cylinder that it would fit snugly inside. It's such a rich text that I'm going to explore it in 4 videos. And this first one will focus on some of the basic points and how Archimedes used them to work out the surface areas of cylinders and cones, and then we'll be ready to move on to spheres next. If you haven't looked at my videos on Archimedes' measurement of the circle yet, then I recommend that you check those out first because they introduce in a simpler form some of the essentials that we're going to cover here. And that includes the technique of sandwiching a circle between 2 regular polygons, one inscribed in the circle and one circumscribed around it. Now, why is this a useful thing to do? There are 2 main points. First, if you give me any number above 1, I can find a pair of polygons where the ratio of their perimeters or of their areas is less than your number. In other words, I can make them as close as you like. And secondly, Archimedes couldn't measure the length of a curve directly, but he was willing to say that the circle's circumference in a figure like this is between the 2 perimeters, just as the circle itself lies between the 2 polygons. So if the perimeters can be made as close as you like to each other, we can zero in on the length of the curve. So let's look at each of those ideas in turn just a bit more. First of all, then, how can I find polygons where the ratio of the perimeters will be closer than any unequal ratio that you set me? So if we consider this figure, we've got the circle sandwiched between 2 regular octagons, just as an example. The octagons are similar, so the ratio of their perimeters is also the ratio of the distances from the center to each edge, so the green and the blue line here. And if we bisected this angle, we could use triangle OAC with its angle of 180 over 16 as the basis of a pair of 16-sided polygons, just as triangle OAB with its angle of 180 over 8 is the basis for 2 octagons. So in other words, OC over OA would be the ratio between the perimeters of inscribed and circumscribed 16-sided polygons, and so on if we bisected the angle at the center even more times. So if you now give me any number above 1, I can represent it as the ratio of some hypotenuse OT to the line OA. In the example in the diagram, the ratio from a pair of octagons is larger than that, so I haven't yet completed the challenge, but if we bisect this angle enough times, we'll end up eventually with a little sliver of a triangle where the hypotenuse will be below and so shorter than the red line, and then we can use that hypotenuse as the basis of our construction, acting as the line from the center to the midpoint, or if you like, the first side in the circumscribed polygon, a bit like the green hypotenuse does with the octagon, and the grey one would do with a 16-sided polygon. Now, as I said, this only tells us about the length of the circumference because Archimedes made some further assumptions about how the length of a convex curve or the area of a convex surface can be measured at all, without, for example, just resorting to, say, a physical method like building a little scale model of every diagram with a rope that you can then straighten out and measure the length of directly. Geometry is meant to be exact in a way that physical measurements are not. So we have to just lay down a reasonable definition of how length operates and then follow through on it. And the assumptions that Archimedes made for that definition are firstly that the shortest distance between 2 points is the straight line between them. And secondly, that if you have a straight line like that and 2 convex paths, one of which lies between the other one and the straight line, that path in the middle will be shorter than the outer path. So in our diagram, there are different routes between the neighbouring vertices of the inner octagon. The shortest route is the straight line, so the side of the inner octagon. Then the circular arc is always between the outer octagon and that straight line. It never goes outside of the outer octagon. And both the curve and the outer octagon are convex shapes. So by the assumption, we're allowed to say that the length of the circular arc lies between the perimeters of the octagons or of any other pair of polygons, regular polygons that we could construct like this. And it's that line of reasoning that enabled Archimedes to make his approximation of pi. Now, on the sphere and cylinder, Archimedes introduced some equivalent assumptions, not for length, but for how the area of curved surfaces works. First, given a closed shape in a plane, a bit like a circle in this example, the smallest convex surface bounded by that shape is what lies in the plane. So that's the equivalent of a straight line in 2 dimensions. Here it's the flat circle. Secondly, if you've got the plane there and then 2 convex surfaces, again with one line between the plane and the other convex surface, then that one in the middle will have the smaller surface area. So, armed with these basics, the simplest curved surface to try and tackle the area of is that of a cylinder. Now, nowadays, the normal way to think of the surface area, I think, is that you sort of snip along the side of the cylinder and unroll it. Cylinder actually means something that rolls in Greek. You unroll it into a rectangle, and the height is going to equal that of the cylinder, and the base of the rectangle is going to equal the circumference of the cross-section, the thing you've just unrolled. Now, that kind of intuitive method isn't up to Archimedes' standards of proof. He does something very different. He sandwiches the cylinder's cross-section, and what we then get is a cylinder sandwiched between 2 prisms. And now the prism surfaces are composed of flat rectangles, so those we can easily tot up the total surface area of. And it's going to be the height multiplied by the perimeter of each of the polygons at the base there. Now, you may think it's then intuitive that the surface area of the cylinder would be between the surface area of those prisms, just like the circumference of the circle was between the 2 polygons. But actually, the assumption that we looked at about measuring convex curved surfaces doesn't quite allow this. In our diagram, what goes without saying is that the bit of cylindrical surface between AD and BC, plus the little circle segments at the end, those taken together are larger than the rectangle ABCD. So what we need to prove next is that actually the cylindrical surface on its own is larger. Now, the way Archimedes does this is he introduces a new line, MN, halfway round the segments, halfway round the cylindrical bit, and then says, well, the sum of the rectangles that we've now produced, ADNM and BCNM, that is in total the height times AM plus MB, and that's going to be greater than the area of ABCD, because we've made a basic assumption that the shortest distance between A and B is the straight line between them. Now, suppose that the difference in lengths, AM plus MB minus AB, suppose that difference is delta. Then what we can do is keep fracturing, if you like, the path AB, so replacing each part to go via the midpoint of the arc, until all the little segments that are left over at the ends get as small as you like. Now, applying our assumption about surface area, what we can then say is that the cylindrical surface area plus all of those tiny little segments that we've got left over is going to be greater than the sum of the rectangles, in other words, the outer surface of whatever prism we have created, and that in turn, it's going to be greater than or equal to the two rectangles that we started out with. If we've had to make a more complex prism, then its surface area is going to be larger, but otherwise it'll be equal to the two rectangles AMND and MBNC, MBCN. So overall, we can subtract on both sides, and we do end up with the result that the cylindrical surface area will be larger on its own than rectangle ABCD. So that's quite a fiddly little argument, but we can do a very, very similar one to show that the cylindrical surface area is less than the surface area of the prism around the outside. And I'm not going to go through that, but you might like to pause the video or think about it afterwards and see if you can get that to work yourself. Only at that point is Archimedes happy to say, well, the surface area of the cylinder is indeed between those of the inscribed and the circumscribed prisms. So what does all of that actually show? As usual, Archimedes' proof goes by contradiction. If the surface area of the cylinder is any more than the height times the end circumference, what we could do is use a polygon with a large enough number of sides that we would get an inscribed prism which is so close in surface area to the cylinder that its own surface area would actually be more than the height times the end circumference. But, as we were saying earlier, its surface area, we know quite precisely, is the height times the perimeter of that inscribed polygon, which is going to be less than the circumference. So that would be a contradiction. And you get a similar contradiction using the circumscribed prism in a scenario that the surface area of the cylinder is any less than the height times the end circumference. So that is actually the only possibility left, that formula that we're familiar with now, the surface area of a tube is the height times the circumference of the cross section. You might say something like 2 pi RH in modern symbols. Now, the other thing that I said we would look at in this video is the surface area of the cone, and the argument is completely analogous. I'm just going to sketch it out, and again, it's something that you might like to check after the video, that you can actually fill in all the details here. So the first thing we do is sandwich the base circle of our isosceles cone with two polygons, and we use those as the basis for pyramids rather than prisms, one inscribed and one circumscribed. The surface area in each pyramid is composed from congruent triangles, and they've got fixed heights, either equal to or just a little bit less than the side of the cone. And so the total area is going to be half times that height times the total base being the polygon's perimeter. And with a bit of care, just like we did before, we satisfy ourselves that the surface area of the cone really does lie between the surface area of the two pyramids. And then we say, well, if we use polygons with enough sides, we can make the area of the inner prism, the inner pyramid, as close as we like to half times the side of the cone times the base circumference. It's going to be as close to that but below it. And we can make the surface area of the outer pyramid as close as we like to half times the side of the cone times the base circumference, but from above it's going to be just a little bit over that. And so again, we produce a contradiction if the surface area of the cone were anything other than that value, half times the side of the cone times the base circumference. And you can actually sort of check this result against that origami style argument that I mentioned with the cylinder. This time, if you cut along the side of an isosceles cone and unfold it, what you would end up with is part of a circle. And the radius of the circle would be, if you like, S, the side of the cone, and the total arc around the edge would be 2 pi r, if you want to use r for the radius of the base. So in other words, it's the proportion of a circle, it's an r over s proportion of the circle radius s. So the total area is pi times the radius times the side of the cone, which is the same result that Archimedes reached. So in this video then we've mainly looked at some of the groundwork on which Archimedes built all of his results about curves and areas of curved surfaces. And we've also looked about how he used those assumptions to measure the surface area of a cylinder and of an isosceles cone. What we're going to move on to in the next video, and I hope you'll join me for that, is watching Archimedes develop those results, especially about cones, and putting them together in order to figure out the surface area of a sphere. So thanks very much for watching.